I thank Jin, Liang, and Lucas for this wonderful workshop together. And well, really my pleasure to get invited again. And well, I don't really care whether it's recognized as a leader or not. I care I'm recognized to be still young. Hope next time I can still attend it. Although, yeah, I don't know who will organize next one. Well, as we learned from Maya's talk, actually this topological phase we realize in many materials. There are already a lot of topological materials. And in this talk, my interest is here. I asked a question about this topological response, like as Adolfo talked about this linear response and the nonlinear response. And here especially, here I will talk about, for example, like if we have a current and we will get spin accumulation here, this is called the spin Hall effect. And if this spin is not balanced, we have a charge accumulation, this is anomalous Hall effect. And this linear response go to higher order, suppose the input is a light, and then actually we can still get a DC current response. Then here, well, for example, anomalous Hall, there are intrinsic anomalous Hall and extrinsic. But here, what I'm talking is mainly about this intrinsic property and dominantly from the band structure. For example, we start from the anomalous Hall. We know like it's well started in many magnetic material from simple magnet to this magnetic wire sand metal and magnetic doped topological insulator. And also for the spin Hall, and in this spintronic community, like platinum is well, maybe the most popular one and used in a lot of devices. And also topological insulator. Well, we know at the beginning topological insulator was called quantum spin Hall insulator. And well, in most of the case, this family, this material, they are not very magnetic. And for this nonlinear optical material, and here is mainly like this is a traditional start, this polar oxide, and recent years experiment theory focus on this non-magnetic wire sand metal. And here I try to, well, you already like a general feature of this phenomena, they are related with this barrier curvature. The barrier curvature here is this omega, contribute to this anomalous velocity. And the only message we need to know the barrier curvature is purely from the band structure effect. You know the block wave function, you know the dispersion, then you have the barrier curvature. But here I try to ask is like, if this system there's a magnetism, especially for the spin Hall or this nonlinear response, and there might be something different. And all here, since now today we have a lot of especially magnetic topological material like this wire sand metal. And then this can do okay if we have a wire magnetic material, we can possibly we have a strong anomalous Hall effect. And but can it do something more? Can it be a platform for us to ask for new questions? And well, here barrier curvature is well established to explain this phenomena, but maybe there could be something different, something slightly beyond the barrier curvature picture. For example, this story started from years ago. We started there in the Dresden Claudia group. We studied material. The formula is Mn3 germanium, and then at the same time there's another team material. First, this is the crystal structure. Most interesting is this in the layer. This big atom is the Mn. It shows a non-collinear AFM structure. In this, actually it's a Kagami lattice. In this triangle, the spin form 120-degree angle. They stay in plane, and this magnetic order is robust at room temperature. Actually, the order temperature is even above 400 Kelvin. Then usually in AFM, we don't expect anomalous Hall response, right? As ordinary AFM, we have a collinear structure. There the spin up and down, this signal totally cancel each other. Or in other language, that means we have a time reversal and a lattice shift symmetry, as Maya explained. And this symmetry involves time reversal, it killed the anomalous Hall response. But in this non-collinear case, this symmetry was removed. Then therefore, anomalous Hall is allowed to come out. Actually, this principle first pointed out by this early paper, and about that time they predict a different material. Then this anomalous Hall is realized in this family, and then that means now we have a material works as a at room temperature as strong anomalous Hall. And my interest is, well, that time I asked maybe we argue magnetic YSM metal has an anomalous Hall. But at that time, we didn't have really a magnetic YSM metal. But now, maybe this material has this wire property. And indeed, in the band structure, we find the YSM metal. But well, actually, this is a wire metal. Means you see the band structure. And this is a typical metal. The Fermi energy cross the middle of several bands. And well, maybe this is another being like a, we call this topological material YSM metal. They never semi. They always very metallic. And others, topological insulator, well, they rarely insulating. But anyhow, this does not stop us like to observe this anomalous Hall, this transport property. And well, this is our dream. Our reality is always more complicated. And here, what I plot here, like these points, they are wire points. In other words, we have many bands in the Fermi energy. This band crossing actually easily generates some crossing points. There are so many crossing points, and then if we go close enough to these points, actually we see this barrier curvature, like show this monopole structure. And well, these details does not matter too much. And first, we ask a question. Since we measured the anomalous Hall of this material, and we see the band structure has a strong barrier curvature, and we ask another question whether this AFM material maybe also have strong spin Hall effect. Although people focus on non-magnetic material before, now this is an AFM. We don't have a total net magnetic moment. Then, in the spin Hall, actually, like usually we assume this is the standard, the textbook linear response. Like we apply electric field, we have some measurable quantity. If this part is the current, then this is, all this part can be the spin current. And yeah, well, this is the standard part. If this is current, and actually here, this part, this is imaginary part from this linear response. And this is the anomalous Hall conductivity. But if it's a spin current, and here actually, if we have time reversal symmetry, and this tells us the second term, okay, is even in time reversal symmetry, but the first term, here, this term, is odd. Therefore, if we have a time reversal symmetry, the first term will vanish. And therefore, in previous work, when people study platinum, like a constant telluride, this non-magnetic material, people directly go to calculate this part. And in theory, and this part actually is the barrier curvature contribution. If it's a spin current, and this part actually, this is the spin current operator, or we call it spin barrier curvature, or spin dependent barrier curvature. And well, now we then look at the symmetry. If you have a time reversal symmetry, anomalous Hall, okay, we care the barrier curvature part. And for the spin Hall, we also care this barrier curvature part because this part is zero. But if we have time reversal symmetry breaking, if it's magnetic, therefore here, because the first part is non-zero. And then that means for a magnetic system, if we care about the spin current, the spin Hall effect, there should be a new term come out. And this new term, well, let's look, this term you see is the real part of this response function. Here, this is related actually, it's the relaxation time. And or it's the shift of the Fermi surface, like the normal conductivity. And if we look close to the Fermi surface, actually, this is the spin texture on the Fermi surface. It's not surprising, you see the spin point here, and when this, suppose we apply a current along this x direction. Well, sure, you see the most current contribute is from the spin along x, right? We can get a current, the spin polarized along x-axis. And this, we can write such a response. And well, but a little different is now. Now actually, we started with the AFM material. There's no mechanization. We apply a current, then the current becomes spin polarized. And this is a little surprise, actually. This is like equivalent. If we have a FM metal, we apply a current. the current is polarized. That's never a surprise. But then this means actually, here we apply a current, this current is polarized. But if two sides, we have a domain wall in between, if two sides we have opposite phase, then here this current will become smaller, this is a Ternary junction. It's hard to turn through. If the two sides have the same phase, it's easy to turn on. But if we change it to FM, it's totally natural, even trivial, right? Magnetic Ternary junction. Actually, we can do the same with this non-collinear AFM structure. And then about the spin Hall, go a little more detail. If we have time reversal, for this one, we consider the crystal, the space group symmetry. And this is, for example, this is one part, the allowed matrix element. Actually, this is for the time reversal even part. And for the time reversal odd part, we have another two contribution. And they are different matrix elements. That means if experiment can mirror all the matrix elements, and you find this term is non-zero, definitely this is only from this time reversal breaking part, the sigma part. Actually, recent experiment, and they mirrored exactly this term out and claim this is a time reversal odd part. Also, experiment can even easier to identify it. You apply a magnetic field, and magnetic field kind of to change this phase from this crystal magnetic structure to another one. You switch, you apply a the time reversal operation. Apply time reversal, this part does not change, or this part will change sign. And then clearly experiment say you reverse the magnetic field, you reverse this spin Hall conductivity. This is a clear signature. There's only contribution is from here. Next, about this, let's go a step more about this nonlinear response. The nonlinear response, well, Adolfo already explained us here. I simply see from this one, the light electric field is E cosine omega, and the polarization we can write to the second order. Then the DC current as a time derivative, actually you can see simply after the omega t, the average, this part is non-zero. We can get a non-zero DC current out. And then actually people know this non-linear response actually observed first in this polar oxide material, and later is tended to start in many other systems. And here, the only precondition is about this required system should break invariant symmetry. And actually, in recent years, well, this is the one organizer, Mr. Chairman's work, and already found that actually tantalum arsenide, the first YSM metal, has the nonlinear response. It actually is the Chi2 part. It's 100 or several 200 or 300 times larger than ordinary material. And then they also built for proposals about this quantized photocurrent. And well, this so far, actually, when I revisit, let's see, actually so far our interest looks really focused on this non-magnetic material, right? Then science for spin Hall motivate us, if it becomes magnetic, something may be different. And then this motivates me to think about a question. Let's just forget the Berry phase and all this complicated formula, even the response formula. Just forget about it. Suppose we ask a simple question. We shine a light to a material. How can we get a DC current? The most simple one we can explain to undergraduate student is, okay, the light generates an electron-hole pair. Band structure tells us the hole and the electron has opposite group velocity. If the lifetime is long enough, we can have a DC current. But this never really work out, because at K you have a velocity, minus K you have another excitation, right? They always exactly cancel each other. At K minus K, the velocity cancel. Then the question is, okay, let's break this symmetry, break the K minus K symmetry. If we reduce, here, if we have invariant symmetry and time reversal, all with the band double degeneracy, if we break invariant symmetry, actually, these two Rashba bands, we still have this symmetry, this K minus K velocity cancellation. Then let's just break both. If we break both, now the band structure left and right are not symmetric. And in this case, we can get a net velocity contribution. Or even go to an extreme case, we break P and T, but we still keep PT, for example. here, all the bands still double generate, but clearly it's not symmetric anymore. And in this case, yeah, like here, these two cases, we can get a non-zero velocity out. And then this is corresponding to a DC current. Then clearly, from this mechanism, the DC current should be proportional to the dipole transition between this valence and the conduction band, and also proportional to the relaxation time, tau here. And this is the dipole transition, also proportional to the velocity difference at k minus k point, these pairs. And yeah, actually, well, actually surprised me, actually, this term, people didn't really recognize it, maybe because people pay a lot of attention to this time orthosymmetric case. And here, this part, you may ask, like, quantitatively, which determines the symmetry breaking between left and right. Yeah. And here, I didn't really talk about the rule of the spin-orbit coupling. Actually, to be accurate, it's exactly spin-orbit coupling determines how left and right they are different. If spin-orbit coupling is 0, actually this still perfect symmetric. And well, for this mechanism, we propose like a system like actually has this PT symmetry. Like if we have two magnetic layers, this is a magnetic insulator. We have this AFM structure, and here exactly like actually the crystal has inverted symmetry, but the spin break inversion, and we have this combined PT symmetry here. If it's fully ferromagnetic, and here we have inverted symmetry. The photocurrent should be 0 exactly, and about in these two cases, we can get a non-zero current because of the imbalance between the K minus chi. This is the DFT band structure. You can see there here. Actually, this side, this gap is still slightly larger. This side is smaller. Actually, this gap is exactly the spin-orbital coupling gap. This, because this P and T both are broken, the left and right, they are not necessarily the same gap. And well, later when I talked to several experiment group, like Fine told me this material actually is very insulating, even you have a photocurrent out, and maybe you cannot really measure it. Actually, by the way, this is a demonstration about this photocurrent from the band transition, and this is without SOC. You see, it's perfect symmetric, and here now you break the symmetry, and we can get the non-zero and the net current out. And this is about a DC current. Actually, the DC current is another second order response, like the second harmonic generation, shares the same symmetry as this DC current. Actually, recently there's another experiment by Xiaodong and Wu, and they mirror exactly the same system, or they mirror the second harmonic generation, and they get exactly the same symmetry one. And maybe this really to see this DC current is very challenging. But here, let's revisit actually this mechanism. Here, I only care is the K minus K symmetry breaking, and I don't really need an insulator, even a semi-metal, or we have PT symmetric Dirac semi-metal, as long as P and T both are broken. Actually, in reality, I think there are many materials, especially these 2D materials, and this is a 3D material. They all have such symmetry, and maybe, yeah, well, this is a question. Experiment will know better which material maybe work. And then, okay, now let's come back to the anomalous Hall again, and later come back to the linear response about the anomalous Hall. You see, this anomalous Hall is observed even to 400 Kelvin. About this material, actually, both these materials, actually, they are really dirty material. They are dirty in a sense. They're not exactly 3 to 1. Even many times there are even 10% defect. And the 10% defect, actually, it means like the electron travel about 10 nanometer, it will see a defect. This is a really dirty case. And also, I said this is a metal, not really semi-metal, huge tensile state. Then the Lorentz force part, ordinary Hall response, just the 0, almost 0. Actually, you see this data, this Hall data, actually is the raw data. It's not remove the linear background, because the linear background is negligible. That means Actually, dirty give us an advantage, and this huge metallic advantage. Whatever we measure this Hall, we will get dominantly the anomalous Hall signal. And you don't have to worry about other competing mechanisms. And then this is a kind of advantage of dirty. Then since this anomalous Hall, it feel the intrinsic barrier curvature from the band structure, then other transport property like thermal and thermoelectric transport, like the thermal, this is the charge Hall, or like the thermal Hall effect, and apply a temperature gradients. And here, this is the anomalous the heat current, and the kappa xy is the thermal Hall conductivity, and this is the nonce is the thermal and electric coupling together. Actually, this thermoelectric transport, they also feel this barrier curvature. And then, actually, in experiment quickly measure this material, this dirty material, you get this thermal Hall. And here, actually, in thermoelectric, usually we ask a question, like, when thermal conductivity and charge conductivity, their ratio, this called this Lorentz number, at a zero temperature limit, and it's a constant. It's constant defined by this Boltzmann constant and the charge. And here, this is at zero temperature for 3D material. Most of the time it's valid, and simply because we have the same particle to bring you the charge and the heat spontaneously. But at the finite temperature, this normal transport we know is get violated. It's not constant anymore, simply because, for example, we have a lot of scattering. This is like electron phonocoupling. Electron lose the energy to the lattice. And here this Wiedemann-Franz law get violated. But now, suppose now we have this anomalous Hall system. We can mirror this sigma xy, kappa xy part. And we always see this, for example, this sigma xy is from intrinsic property. Now depends on scattering. Now depends on tau. And well, this part becomes really robust. If it's robust at finite temperature, does it mean this should be a constant always? And well, naively, maybe we believe, suppose ideally it's purely intrinsic, and we have this intrinsic contribution, it might be a constant. But let's see how experiment get. Actually, experiment here, the experiment was done by Carmen Benia. And yeah, actually, at the beginning, his experiment motivated me to think about this question. And he measured these two materials. One is this tin material, another is germanium one. For me, at the beginning, from band structure, it looks almost the same. I never imagined these two will make some qualitative difference. But in experiment, clearly, this tin material, this anomalous Lorentz number is always flat, always almost a constant up to room temperature. And about the germanium one, easily just go away from this constant around 100 Kelvin. And that's, well, where surprised me. Always the first question they ask, how important the ordinary scattering, yeah? Maybe still matters. And to observe the ordinary scattering, this is the longitudinal resistivity. It's dependent on the temperature. This is a standard way, like if we have electron phonocoupling, the resistivity increase as the increase in temperature. And actually here we see germanium and tin, these two compounds, they look very similar. Actually, if you want at least at 100 Kelvin, there's nothing strange happen. And this part are not like, we don't see a direct correlation between this violation and here, the scattering part. The science, okay, and here we talk, this part is intrinsically from the barrier phase, from the band structure. And let's see a little more close how it's related with the barrier phase. And this is the barrier phase. We sum over the barrier phase below the Fermi energy. And this is a zero temperature case, actually. Here, this is the chemical potential dependent barrier phase. And well, here, this sigma xy at finite temperature, actually this part, just a dirt function, only means it take the barrier phase at the chemical potential 0, and we get it. But for thermal, because here thermal is energy flow, and we have an energy square here. This is a very important difference. And this part is the same. Here also we know at 0 temperature limit, this thermal conductivity exactly go to a constant with this charge part. That means at zero temperature for this formula, Wiedemann-Franz law is solid. At finite temperature, what happened? Well, this blue part, this factor is a Dart function. At a finite temperature, we have some broadening. This part, we have the energy square. It becomes a double peak function. This double peak, the peak distance is the energy difference. Then now immediately we know, like actually, suppose if this part is a constant or almost linear in this way, actually these two integral, their ratio will be always like this Lorentz number. And this is simply a way of how to integrate this sigma xy part. But if we have some special case, very nonlinear, and we get this part, and that means the electron, this integration will fill the center part, but the thermal will feel very far from the Fermi surface. That means they pick up a different part of the Fermi surface. And then in this case, we don't have to assume their ratio will be constant, right? And actually, simply for this, now we compare these two materials. Actually, this is the ab initio band structure. This color you see is the Barry curvature with a different sign. The blue and the red, they're the opposite sign. And this is the energy dependence. This is the chemical potential, and this is the sigma xy value. You can see it first. For the T material, it's relatively flat for energy. And for the germanium material, actually, there's a small peak here. And actually, the distance between Fermi energy and this small peak is in the order of this 100 Kelvin. And then it's not surprised this germanium one easily go away from this Lorentz number. But this one, this flat one, just like we have a constant in this integral. Okay, you may ask, like, why these two materials can be so different? And if we look at the formula slightly, now roughly we can rationalize in a way. Germanium and tin, germanium has relatively weak spin-orbital coupling. If SOC is strong enough, we have valence SOC will increase this gap, right? This anti-crossing gap. And this anti-crossing gap will become larger and larger. Another consequence is then the Barry curvature is smeared. It's smeared in momentum space and in energy. Therefore, the tin one, in the end, is smeared more, becomes more average distribution to energy. And this one easily, we have some small gap, we have some jump. And in this sense, we have one more possibility, like to violate the Wiedemann-Franz law here. And I think now I'm done. This is my summary. And let's see, this time was breaking up that actually motivate us to think some slightly different new contribution in linear response and nonlinear case. And in the end, I thank my collaborators, especially here with Fernando, and helpful discussions with Liang Wu and Adolfo. And good, thank you for your attention. Questions?
So one thing that I noted in your resistance measurements when you compared the two manganese, tin, and germanium is that there seems to be in the germanium an upturn in resistivity, right? I mean, it's somewhat unusual at around 200 Kelvin that you have something that on the one hand is order of 100 micron centimeters, so it's a rather good metallic state, and at the same time it has, technically speaking, an insulating temperature behavior. Right, it increases as you cool down.
This slide.
That's right.
Yeah.
That is, if you think of anything phonon scattering related, really non-trivial. And it somewhat happens in a similar temperature range. So I was wondering if you could make a similar type of density of states argument that somehow, even though you sharpen the Fermi-Dirac distribution and you reduce the number of phonons, you still get an enhancement of resistivity as you cool down. And that it's somewhat of a still a semiconductor-like effect of shrinking this out of some higher density of states.
Yeah, but somehow I think this system is super metallic.
But then why does it do that?
This behavior also very anisotropy. If you change the current direction, say from 100 to 001, the behavior also changes.
To what do you mean change?
Resistivity behavior changes. Temperature.
its amplitude will change or it's totally qualitatively different.
This hump behavior.
Yeah.
So it changes actually. So one case it's very sharp, another case it's more flat.
Okay, maybe.
Yeah. So, because the talk is about topological magnetic materials, I think half of it doesn't really relate anymore to topology. Does it? Is that the,
Not very necessary.
yeah. So is that the trend? So is that what we can take away from here? That topology maybe leads us to think about other directions.
Yeah, all I would say, like, for the sake we studied topological material, and actually for this, we revisit many old material and create new material. This is well, this is in this platform, there's a new question come up.
So these magnetic photovoltaic effects, very interesting. So do you understand what happens when in the clean limit when tau goes to infinity?
Tau go to infinity, then you have infinite large current.
Yeah. So
Yeah. Actually, this is well, I didn't say this light. I don't assume it's a circular polarized. Actually, it's a linear polarized light.
Right.
And actually, this is you would get an injection current from linear light.
yeah. So do you know what happens as it becomes cleaner and cleaner?
You mean tau go to infinite? Yeah, then you get a super large current. Yes, I assume. But like injection current, we never see the injection current. Yeah, infinite.
So, yeah, I have one question. So in principle, I think this kind of magnetic photogalvanic applied to manganese bismuth tellurium with even layer, right?
Yeah,
Brick T, but-
yes. This AFM structure.
So then, in that case, you also have surface state.
Right.
Yeah. So then,
You have a gap to surface state.
no, it's anti-ferromagnetic.
Yeah. But then because the timers of break, the Dirac state opens a small gap. That's people claim, but actually ALPAs didn't really find it.
So anyway, I'm curious. So if this kind of photogalvanic effect happened during the surface state band, are there some new properties?
New property? Yeah, very good question actually. This means your question is simply like if we're for this 2D band. Yeah.
Yes.
I think in this 2D case we break inversion clearly because it's surface. And timers are breaking, and you will see the same effect. Or in other words, this is not limited to insulator metal and even in a metal case, as long as you align it.
Any other questions? Okay, if not, let's thank Binghai.
Thanks.